questions on the last time?
So just a quick question on the very last thing that we did. That our guess is that the exponents will be the numbers coming in the equation summation negative infinity negative 1 to the power n q to the n by 2 thing, and then we expanded it to like summation n is equal to 1 to infinity negative 1 to the power n q to the n by 2 3n minus 1 plus q to the n by 2 3n plus 2. Uh, my question is, so when we take negative numbers as inputs, would our kind of like, we are kind of summing over the like the sum of both the entries. So like would they match up? Like I was not too sure.
So this is the formula we are looking at, right?
Yes, professor.
This one.
Yes, professor.
So at n equal to 0, you have 1. And for, let's say, n going from, for n negative numbers, you replace n by minus n, and you will get plus n here. So when you are doing negative numbers, this will come up. So you replace n by minus n. Then you'll get n by 2, 3n plus 1. And this was already there. So they all match up. I mean, they match up in this case.
Right.
Does that answer your question?
Yes, professor.
Okay, so today, so this is where are we? Lecture 15. It doesn't sound like much, but to me it seems like we've covered a lot. So the agenda is Euler's pentagonal number theorem. We want to prove it, and we also want to do maybe something on products, infinite products. So we've done, I mean, from what I could tell, you guys have done a lot of series, but haven't done any products. So we just note down a few theorems. Anyway, so this was the formula which we were looking at. Q infinity equal to 1 minus q square, 1 minus q cubed, and so on. And this is n going from, this is one way of writing it, minus 1 raised per n, q raised per 3n square minus n over 2. And the other way of writing it, we just saw, was like this. Okay. N 3n plus 1 over 2 plus q raised per n 3n minus 1 over 2. Okay, and we also know that if we just multiply the things together, this would be 1 plus, you take the partitions of n with distinct parts plus even parts, and you subtract the partitions of n with distinct plus odd parts, and you multiply by q raised per n. So this business right here. So this is kind of obvious. You just multiply them together. If you pick up the n, then there is a multiple ways of writing this as even parts and maybe odd parts, and you subtract. So what this theorem is saying, that more or less these guys are the same, except for a few values. And how does one prove this fact? So we will do two proofs of this, but today we'll do one. Proof is due to Franklin. This is 1880. Okay. Um, so, um, so in any so what he does is, I mean, the basic idea, he makes an involution. So he takes this set uh, of partitions of n with distinct and even. So he takes all these partitions and he connects them with the other guys where they are distinct plus odd. And he's able to send one to the other and other to this one, except in a few cases. And so you have an inverse mapping, but except in a few cases, which happen to be these guys. So there's always they're always equal except for few exceptional cases. That's the idea. So in any partition of n into distinct parts, so let's make a usual proof by pictures. You look at two statistics. So I look at two statistics. So this is a partition lambda 1 bigger than lambda 2, bigger than lambda 3, and so on, up till lambda, let's say, q. Well, q is a bad idea. Lambda something k bigger than 0. So these parts are distinct. You look at this guy. This is lambda k, the smallest part. So let smallest part be r. So this guy. And you look at this, the longest uh, sort of set of number of points with slope -1 from the right. So let S be the largest. I mean, it's easy to see what it is. It's the largest number such that if you take the difference between lambda 1 minus lambda 2, lambda 2 minus lambda 3, until lambda s minus 1, then this is the largest such that the difference is exactly 1. Okay, so the largest s such that this happens. So in this case, s is equal to 2. So lambda 1 minus lambda 2 is 2. So is this clear what these two guys are? So definitions are clear.
Yeah.
So, and the involution, so what you do is, involution is simply a map going from one to the other and then coming back. So the involution is, you take, suppose S is less than R. So suppose you have this situation again. So this is 2, let's say, and this is 3. So this is, here S is 2 and R is 3. So if S is, if this is less than this, then you bring these guys down. So you bring them over here. 3, 4, 5. 1, 2, 3. Oops. Shouldn't be in a hurry. 2, 3, 4, 5. 1, 2, 3, 4. Okay, so if S is less than R, then I bring this over here, and otherwise, if R is less than or equal to S, that means this is smaller than this, then we bring this over here. So let me do an example here. This is 3. Okay, so now what we do is we bring this chap. So here R is equal to 2 and S is equal to 3, and we bring it over here. And it could be equal to. So what we do is we bring it here, bring it over here. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. And I bring these here. Fine. So what happens is that when I bring it, so this was, if it goes, if it was odd, then it will go to even, and you can go vice versa, right? If you have a smaller one than this guy, so here the number of things are 1, 2, 3, 4. So you can bring it over here, or so this is an involution. So you can go from odd to even parts. So odd number of parts to even number of parts, right? So they match up. I mean, we are doing summing over number of guys with even parts, number with odd. These will cancel. And again, same thing here. 1, 2, 3, 4, 5. So again, odd will get mapped to even. Okay. So this happens most of the time, except two cases where it doesn't, where we can't do this.
Sir?
Yeah.
So we are considering distinct into even number of parts, not even parts.
Yes. Yes.
Okay.
The parts themselves are odd and even, and they are distinct. So the parts are distinct and even. Yeah. So when you multiply this guy together, all the parts are. Uh, uh, okay, I see what you're saying. So you multiply, when you multiply all this, then the number of parts is even. Yeah. Number of parts is even. Yeah. Does that clarify?
Yes, yes, Professor.
Okay. So if it has odd number of parts, it goes to even. If it has even, it goes to odd. And so they cancel basically. And there are two cases where we can't do this. So what are those two cases? Two cases are one, when R is equal to S and they meet. Meet meaning this and this meet. Like this over here is meeting. No, this one was meeting. But here R has to be equal to S. And if that is the case, then so some case like this. So 3 here, 3 here. So here R is equal to S, and they meet, right? So in this case, the partition is this number is the same as S. Then you have S plus 1 and so on, and there are S parts. So S plus 0, 1, 2, whatever, S minus 1. So this is S squared plus 0 plus 1 up till this. So this S into S minus 1 over 2, or S 3S minus 1 over 2. And the other case is when R is equal to S plus 1 and they meet. So this is the same. So this kind of situation. So you have S equal to 3 and R equal to 4, and they meet. So now, so the problem is this, that in this case, we would have brought this upwards, right? Because R is less than equal to S, so we would have brought it upwards. But then, since they are meeting, since they're equal, this you can't do it. It'll come. I mean, there's not enough empty spaces available. And here the problem is this, that if you bring this over down here, so here S is less than R, so you have to bring these downstairs. But if you bring them downstairs, they're equal. So they don't remain distinct parts. So this is a problem. And in this case, the partition, it's a partition of. So this is S plus 1, and then you're doing S plus 2, and so on up till S plus, there are S parts, 1, 2, 3 up till S. So this is S square plus 1 plus 2 and so on. So it's S over S plus 1 over 2, which is S, and then 3S plus 1 over 2. Now the number of parts in this case is S. So this contributes, so this sign contributed by this guy. So this is left extra. This is left extra. It's not mapped in the involution. So the sign contribution is minus 1 raised for S. And same thing here. This is the, the sign contributed by this guy. Because there are exactly S parts in here. So here, let's call this process 1. I'll use a third color. Okay. And let's call this process 2. And this is a problem for process 2. This is an exception for process 2, and this is an exception for process 1. And you can see that if this is not the case, you can map it, and it does map. So if they don't meet, then it can come here, and vice versa. This can go down there, and same thing you can check over here. That if they don't meet, then you can do whatever you're supposed to. So just this much, for example, would be a problem. Okay, so what does this mean? This proves it actually. So the number of n in distinct and even parts is equal to distinct and odd number of parts unless n is equal to one of these two guys, s 3s minus 1 over 2, or n is equal to s 3s minus plus 1 over 2, in which case the sign is minus 1 raised per s. Sign is, I mean, if it comes from an odd number or an even number, s is the number of parts. So here s is the number of parts. So what do we get? So of course, so that means that if you do p of n blah 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 minus p of n blah blah blah, and let's just keep one outside, q raised per n, then this will be equal to 1 plus n equal to 1 to infinity minus 1 raised per s, q raised per s 3s minus 1 over 2 plus s 3s plus 1 over 2. That's the proof. Okay, any questions?
Professor, the sign part I'm a little confused about. I didn't get it properly.
So for all the non-exceptional cases, odd and even are cancelling. So all those partitions are cancelling, right? So there's no sign there. The exception case, in this case, there is a sign. Now, in this case, the partition which is left over, which cannot be mapped, is a partition with s parts. So if s is odd, it will give minus 1. If it's even, it will give plus 1. So the sign contribution to the sum from this guy left over is 1 minus 1 raised per s. And same thing.
Okay, okay, okay.
I mean, s is the number of
Okay, okay.
parts, right? And we are taking, we are taking plus 1 for when the number of parts is even. So you're multiplying all these guys. If you multiply even number of them, you're going to get plus 1. If you multiply odd number, you'll get minus 1. Is that okay?
Yes, yes, Professor.
This is one of the most beautiful proofs ever, I think. It's in, I mean, anywhere in math, I would say. Do you agree?
Professor, just a small clarification. It is even number of distinct parts minus odd number of distinct parts, or odd number of distinct parts minus even number of distinct parts?
Well, in this sum, in this product, when you multiply this product, then you will, suppose you get something like q raised power, 2 plus 3 plus 5. Then what is the sign which will come? Sign will come from this minus 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 3 times, right? So
Right.
if the number of parts is odd, then you'll get minus sign. Suppose you get a contribution for 1 plus 4 plus 16 plus I don't know, 17. So there are even number of parts here. Then the contribution will be raised per 4. So then you take all of these and you combine the n's together. That's the idea. You collect powers of n.
Right.
So even will come with positive sign, odd will come with negative sign.
Right. Makes sense.
Yeah. Okay, so this is a classic proof. This is a fantastic proof. This is not due to Euler, uh, even though Euler discovered it. And this is often the way. Uh, this is often the way that we discover things analytically, and then we say, does this mean something, and can we give a nice proof of it? And this proof is like, I mean, this is mind blowing proof. I find I don't know, when I first saw it, I thought, wow. This is really mathematics, and really we didn't see it in undergrad. So you are sort of, I mean, things have modernized. In my times, combinatorics was not considered real mathematics, and at that time there used to be this big fight. I mean, that, is this really math? I mean, this is so easy, proved by pictures and so on. And of course, the combinatorics guys were saying, "What all nonsense you guys are doing? Uh, that can't be math." So anyway, this is now, of course, combinatorics is well established as a very big this thing. If you see that Bhatia wanted me to teach a course in combinatorics, which I think would not have been imaginable actually 30 years ago. In even I mean, discrete math, yeah. I mean, computer scientists are always saying, yeah, we need discrete math and all that kind of stuff. So in India, for sure, it wasn't there. In the US, it was quite well established. And of course, computer scientists were asking for such courses because Knuth had written a book in the late 60s, starting from late 60s. And he had included a lot of these things. This was called the art of computer programming. So he had included a lot of stuff I mean, most of the stuff from combinatorics. He felt it was going to be useful for computer science. So a lot of combinatorics was included here. Okay, so there's an interesting story. Yeah,
This will be the summation will be over S, right? We are ranging n from
right. You're right. So going on, there is a um, recurrence relation and an algorithm which Euler wrote for calculating the number of partitions of n. And basically, this is the idea. So he took 1 over QQ infinity, which is the generating function for partitions, right? So this is P0 plus P1Q plus P2Q square, and so on. And then there is QQ infinity, which he just calculated as 1 plus n going from 1 to infinity minus 1 raised per n, q raised per n, 3n minus 1 over 2, q raised by n, 3n plus 1 over 2. Right? And if you multiply the two, what do you get? So you get 1. You should get 1, right? So you multiply this whole thing, and let me write a few terms. I should remember them. I use them so many times, but I don't remember. It's not so difficult to remember. Hmm. So if you multiply them together and take compare coefficients of q to the n for n bigger than 0, so n equal to 0 you'll get 1, but n bigger than 0 on this side you'll get 0, and here what will you get? So if you take q raised per n term here, you will get p of n. Then you will get an q raised per n from this guy, so you will get p raised per n minus 1. So if you have n minus 2 term here, you will multiply it by this guy and get p of n minus 2 plus p of n minus 5. Do you see what I'm doing? Do you get this? This is okay? So here, for example, if I've got n minus 15, p of n minus 15, suppose somewhere here I have p of n minus 15, q raised power 15, then I will multiply this chap, q raised power n minus 15. Then I just multiply this chap with q raised power 15 here, and I will get with a minus sign p of n minus 15, which is what is over here. Right? So it's not an infinite recurrence because n is sort of, you know, um, n is some fixed number. So you're just reducing the numbers by 1, 2, 5, so on. So in fact, this is a you know, as good, almost as good as far as I know. This is the, you know, still. I mean, this is a small question mark, maybe the best possible algorithm. And this is order n square basically. I mean, you know, you have to calculate about a square of the numbers before calculating n. So it's not so difficult. It's still probably the best possible algorithm for computing E of n. And I advise you do so. So use Sage and star to compute P of n for n equal to 1 to 200, let's say 200, and arrange in the following form. So arrange in 5 columns. So, you know, n equal to 1, then 2, 3, 4, 5. Then you do 6, 7, 8, 9, okay, and so on. And the story is McMahon used Euler's recurrence and computed a table as above. And then Ramanujan saw it and conjectured some theorems, which they eventually proved. So he just looked at it and then he started conjecturing stuff. He saw some pattern. So I want you to generate it and then see if you can spot a pattern. Okay. So when I say exercise, most probably I will put all these exercises in your assignment, um, plus some more, but mostly these. So go ahead. And I should mention that I'd given a way to get this, you know, bunch of AIs basically. I mean, how to get a formal power series, a formal polynomial ring with with a large number of variables, so that you can sort of. So this was an answer to Ayush's query last time. So just check on Google Classroom or your email, and then you can use that code for anyway. So any questions so far? So let's do some theory, some pending theory from infinite products, which I should have done before, but I mean, at least something nice you should see every day. Okay. So the this is infinite products, and there are two, three places which is very nice, some references. Um, there is a book by Rainville. This is special functions. Then there is a book by Andrews. This is called number theory. This has a nice appendix. So Andrews is the leading expert in the world of partitions. So he has a number theory book, which I mean, which I read when I was in undergrad, and it wasn't so popular anywhere else except in India. And so our teacher used it, and it had a combinatorial view of number theory. So everything was combinatorial over there. So Andrews was Rademacher's last student. Hans Rademacher was a famous number theorist, analytic number theorist, and then Andrews took over. He's a leading expert in partitions. And there's a third book by Andrews, ASCII, and Roy. This is also called Special Functions. So these two guys are basically the gods of special functions. And Roy he's an Indian mathematician. He was, I think he just passed away. And he used to attend ASCII seminar on special functions a lot, and he basically put the book together. These guys were like, always talking about writing the book, and then he helped them put it all together. So a lot of the ideas are from ASCII, but Roy cleaned it up. And okay, so this idea which I gave you about how to discover, this is also from ASCII's notes. So ASCII used to teach a course. He, he taught a course in Wisconsin called Special Functions. So there was a number, Math 805, Special Functions. So one of ASCII's students is a very good friend of mine, so he gave me the notes. So apparently ASCII gave him a set of handwritten notes saying that, because he missed that class. So he was attending the lecture, and then he just gave him those notes and said, you can look at these. So those notes have taught a lot of people actually, and I'm also reading. I've just so both ASCII student Sean Cooper and I are actually trying to edit them and put them together, but we are taking a lot of time. Anyway, so here's a definition. So I'll do the, actually, even in your complex analysis course, whenever you take it, or if you're taking it concurrently, I seriously doubt if they will cover this. So whatever I tell you today is a little bit to be taken a little bit informally. So let Pn be this, and I'm not going to give, very detailed proofs, but these are very useful things to know. So let Pn be set this product, and if limit n going to infinity of Pn exists and equals some number which is non-zero, then we say the infinite product converges to P. Okay, and so the infinite product is 1 plus ak, k going from 1 to infinity. And some notes. We want to more or less avoid the places where it's zero. So if one term is zero, for example, then the whole thing is zero. I mean, then it's a sort of trivial kind of thing. So if only a finite number of factors 1 plus ak is 0, right? And if the product with those factors removed converges, then we say the product converges to 0. So this 0 is a sort of issue. We want some products to be 0, but then what does it convergent mean? I mean, whatever the other terms, the answer is 0, right? So let's remove it, start from some point onwards. If it converges to something which is non-zero, then we say that okay, it is equal to 0, it converges to 0. And when discussing convergence of products, we usually these ignore such 0 factors. So we say, okay, let's leave that aside and then look at the convergence of everything. And if it does not converge, we say it diverges. This is no big surprise, right? And if p happens to be 0, right? So we're saying if it converges, but then it converges to 0, then we say it diverges to 0. Okay. And one necessary condition is if the limit of Pn is P and it's not 0, then the limit of An has to be 0. Why? Because Pn over Pn minus 1, if you take this limit, this is 1 plus An, and this is going to be 1 because limit Pn is non-zero, so whatever, it's the same P over P. So it's P over P, which is equal to 1. Right, so this implies that it's the limit is 0. So it's like similar to your um, necessary condition for the series convergence. So theorem: if no an is equal to minus 1, then 1 plus ak and summation log 1 plus ak converge and diverge together.
Professor,
Yeah.
I didn't get why limit Pn by Pn minus 1 has to be 1.
Well, limit Pn is P. What is the limit Pn minus 1?
Okay, okay, okay. P again.
So same, right? So this is the theorem. Now here there is this thing which I'm a little bit in trouble because I didn't say that complex analysis is a prerequisite, in which case the course wouldn't have run, because apparently complex analysis happens only in the third year. So this log can be taken. So the log means principal value, and because we are taking complex numbers. So what does that mean? So most of you have taken. So log, of course, you must must have discussed, right, in Preetham's class?
Yes, Professor.
Okay, so yeah, uh, so basically it's they look at it as an inverse of e raised per z. So log of z, because e raised per z is periodic, so there is this log of z has to be log of an absolute value plus some argument, right? And when we say that this is zero, I mean, when the argument is the normal one, then it's the principal value. Okay, so I won't go much into that. If you don't understand it, doesn't matter. Um, think of it as a real part, and then whatever happens in log will happen at some point. So the proof is as follows. So let Pn be equal to, and again I'm going to hand wave a little bit here, 1 plus a k, k going from 1 to n, right? And let Sn be the sum of log 1 plus a k, k going from 1 to n. So then the limit as n goes to infinity of e raised to the power Sn, this will be the limit. I mean, this is the definition, n going to infinity. And this, if we take e to be continuous by continuity, this is e raised to the power limit of Sn, n going to infinity, right? So if the limit Sn exists, then this for sure means that limit Pn exists. Okay. Vice versa, if limit Pn exists, this requires a little bit. So this requires art, some artistry. So, I mean, the right word is in Hindi, but this is what it means. This requires some kalakari, which I won't do, because we want to show that so log z is equal to log of z plus I argument of z, and then we want to show this doesn't matter much, when we are taking the logs. So this is okay. This is by definition. This is fine. But the other way around, there is some logs you are taking, and then the logs should not matter. The argument shouldn't cause any problem. So you can see Andrews, ASCII, and Roy for an argument. For details. Okay, so Rainville doesn't give any details, so it's no point going there. Okay, what is most important for us is absolute convergence. If you remember, absolute convergence used to imply convergence in series. So this is very important. This is the definition. The product 1 plus AK converges absolutely if the series log 1 plus AK converges absolutely. So this is the definition. So now, I mean, now you're in sort of safe territory because the arguments don't matter. And we, of course, assume, since log of 0 is not allowed, all 0 factors are deleted before you take this stuff. And now there is a nice theorem which we will need. The product So this log business, I mean, it causes a little bit of problems in managing things practically. So this absolute convergence theorem is very nice, is absolutely convergent if and only if summation AK is absolutely convergent. Okay, so proof, again, we assume no AK is equal to -1. Node is -1. Okay. If AK is small enough, then we have this power series expansion, which we will use. Okay. So this is valid for AK less than equal to 1. Less than 1. So power series expansions you have done, right? You just said you've done analytic in complex analysis. Okay, since AK goes to 0, there exists a K0 such that K bigger than K0 implies that AK is less than half. So let's just, for consider K bigger than K0, consider this guy, log 1 plus AK over AK minus 1. Okay, so I'm dividing by AK and then subtracting this 1 over here, right? And this will be equal to, uh, well, the absolute value of this business. So AK, I'm dividing by AK everywhere. So AK by 2 minus AK cube, AK square by 3 plus 1. And this is less than equal to AK raised power m over m plus 1, where m is going from 1 to infinity, right? This is an absolute value. And now this is, all of these 1 over m plus 1, I guess they're, you can write this way. So yeah, so certainly 1 by 2 is bigger than 1 over m plus 1. And now we assume that all of them are less than equal to 1 half. So this is 1 by 2 raised per m plus 1. And this is 1 by 2. So it's 1 by 4 plus 1 by 8 and so on. You get 1 by 2. Okay. So what does this mean? This means that the absolute value of, so this chap right here, this means that log of 1 plus AK over AK, it's not very far from 1. So it's bigger than 1 by 2 and less than 3 by 2. Yeah. So what does this mean? This means that log 1 plus AK over AK is less than equal to 3 by 2, and AK over log of 1 plus AK is less than equal to 2. So, now by comparison tests, this is less than equal to this, and this is less than equal to that. So by comparison tests, both follow. Means that log 1 plus ak is absolutely convergent if and only if summation ak is absolute. Yeah. So the second one, if we use this one, we'll know that if this is convergent, then this is convergent. If we use this one, we'll know that if this is convergent, then that is convergent. So yeah, both of them are. Any questions on this? So this is a nice test, and in particular, what we are mostly interested in is this guy. Right? Because this is equal to 1 minus aq to the k, with k going from 0 to infinity. This is absolutely convergent if and only if summation q raised per k is absolutely convergent. And this is your favorite series, it's a geometric series. This converges when absolute value of q is less than 1. So this is what we want essentially from this whole game. That is why I was doing all this stuff. Okay, just we can consider, like we did in real analysis, we can consider.
Professor.
Yeah, yeah. Any
So
queries?
we have a factor that's so we have an a factor there. So shouldn't we have mod q less than 1 by a or something?
Yeah, I mean, we just want this to be convergent. So if you add 1 there, it will still be convergent. I mean, if you add a constant, it will still be convergent for q less than 1.
Professor, because oh
Okay, I'll tell you what you say. This is convergent, right? Because this guy is less than 1. Now, if I multiply by 10 raised per 100, will it still be convergent? Yes, because this guy is.
yeah, that
This
makes sense.
doesn't matter. And this is your A. This A doesn't matter. Is that clear? Am I clear?
Yes, Professor.
I mean, yeah, it's okay. So next we can consider functions. I mean, we can consider, k equal to 1 to infinity of 1 plus a and z, where z is a complex variable. And we can define usual convergence pointwise and so on. The infinite product, this guy, converges. Well, let me explicitly say where z is a real or complex variable, converges in uh, uniformly in its domain. So when it's pointwise, you can just use the previous guy. If the product, I mean, if Pn equal to k going from 1 to n, this should be k 1 plus ak of c converges uniformly. I mean, then you can apply the previous things for all z and so on. So uniform, remember uniform, what does it mean? Uniform just simply means that in that domain, whatever that domain is, only one epsilon and delta, I mean, one epsilon will work essentially for all the points. That's all. So, so it's a very stringent kind of requirement, but we don't have to worry about point wise. Does it converge here, there, whatever. If we know roughly speaking, it converges. And um, so we know that if it converges pointwise in a compact setting, in a compact set, then it converges uniformly. So that's also very helpful. So I think you know all this stuff, right? So things become easier when it's a uniform convergence, and that's the reason we are sort of doing it. And again, zeros. So now zeros, we want our functions to have zeros. Zeros are an issue. Okay, we would like our functions. I mean, functions with no zeros. So, I mean, you're studying that um, in complex analysis. So, entire functions with no zeros are like exponential functions. That's all you have. Or some relative of exponential functions. So you want some, no, in fact, they are e raised per some entire function. So they are not very interesting. So we want our function to have zeros at certain points. So, I mean, we delete those points. So we say that a product I mean, point-wise, if and only if at most a finite number of points, uh, finite number of factors are zero. So here also there are problems. And if by deleting those factors, it converges to a non-zero limit. Okay, and then there are other things. I mean, the zeros at various points of the domain. So, you have some theorems there. Okay. Anyway, so these are issues to handle and to sort of figure out the what to do in the zeros, and we'll see some examples immediately. So if a series summation a and z uh, converges uniformly, in a region, then the product, I mean, we are using the previous theorem. So you want uh, 1 plus a and c does 2. So absolutely convergent series, I mean, the proof is omitted. But as a corollary, if a and z is analytic in some region, region, what is region? You remember what is region? I think open plus connected or something. Am I right, or is there something else?
We did path connected, Professor, like open plus path connected.
Yeah, okay. Path connected. I mean, what is connected? Connected is not path connected.
Uh, Professor, we did. The region is a domain, is specifically that the boundary of the domain is a piecewise piecewise connected uh, curve. That's the boundary of the domain.
Okay. So the boundary of the domain has to be piecewise. It doesn't make sense. Anyway, so yeah, so Pritam, Pritam knows better. Let me hand wave my way through this. But if it's analytic in some region of the complex plane, and analytic, you know, right? And the P of z is equal to 1 plus a n z, n equal to 1 to infinity, converges uniformly in that region, then P of z is analytic. So, I mean, in complex analysis, a lot of these theorems are proved for series. And what we do is we take these products and we just, uh, use the series to get our answers. And analytic means there's a power series expansion, and that means that there is a infinite number of derivatives exists. So holomorphic, right? So all kinds of nice things. Zeros are isolated, and all those nice things happen if this happens. So yeah. So and we are bothered about some region. I mean, around Z, you can always find and so on. All right. So we have some time left, which is wonderful. So here is some more hand waving. Don't try it in your exams. With Pritam, with me you can try, but don't try there. So this is the wonder. This is why I like complex analysis. This is not a. I mean, you might see this theorem at some point. So what do we do? So we know. I mean, this theorem, whatever we have, is very practical actually. Uh, so anyway, we know that if a polynomial uh, has roots, let's say at x equal to 1, 2, 3, let's say, right, just three roots, then it is of the form, p of x is equal to some constant times x minus 1, x minus
Uh, Professor, one question.
2. Yes.
What does holomorphic mean?
Okay, so you haven't done holomorphic.
No,
What
not
is it?
precisely.
Holomorphic means differentiable, basically.
Okay.
Professor,
It
isn't
means
it the
all
same
these
as
things. If it's differentiable, then this happens. If that happens, then that happens. That's the whole point of uh, you know, our course.
Professor?
Yeah.
Isn't it an alternate name for analytic?
No. Yeah. I mean, all these things are equivalent, but analytic usually means power series expansion. Holomorphic usually means as a derivative.
Okay.
And if it has one derivative, it has a million derivatives. So that's the wonder of our complex analysis. One of the
So
wonders.
Professor, does holomorphic extend to higher dimensions? Is that what it is?
Higher dimensions, I don't know anything about. I don't know. Complex, I mean, the complex plane is, a oddity, a brilliant oddity. I don't
Right.
know. I don't know enough of maths to know what happens in higher dimensions. In the complex plane, these things are very beautiful and elegant. So, yeah. So I'm giving you an example which is like mind blowing actually. I mean, it blew my mind when I saw it. So just hang on. So, so you agree that if a polynomial has these three roots, then it looks like this, right? Yeah.
Yes, Professor.
So, what about something like sine pi z? I mean, where are its roots? So roots are, 0, 1, 2, 3, so on, right? And also -1, -2, -3. So can we write sine pi z as z times z minus 1 times z minus 2, so on, and then z plus 1 and z plus 2 and so on? Well, our theorem suggests another format. What our theorem suggests is that we write it like this: z over n and 1 plus z over n. But this, forget about this. I mean, I'm going to write it over.
Professor, n over z, right?
Well, at z equal to n, this is 1 minus 1, which is 0. So our theorem suggests that we write something like this, but there's a problem because log of 1 over z over n, I mean, summation 1 over n for a fixed z does not converge, right? But here's a trick. What you can do is you can combine the two terms and make it z square over n square. And now this guy converges, right? So now this product will converge, okay? And the question is it equal? And well, in my calculus class, Ayush has been helping people there. This limit is 1. So if you put z equal to 1 and multiply and divide, I mean, you would expect a pi over here, right? And indeed, this is true. This is a bona fide theorem in complex analysis. And it's very practical, actually. See, I'll give you another idea. So suppose we just had 1 over z over n, right? Suppose we just had this guy, right? Now, this will, this is a problem, right? So you'll have z over n minus plus something, z square over n square and all. So when I sum over all this is the problem guy, right? Yeah. These guys will converge. This sum will converge, n cubed will converge, and so on. But z over n won't converge for a fixed z. So what I do is I just add a z over n here, e raised per 0. Now if I take logs, what will I get? I will get plus z over n. So I cancel this guy, this chap. Then I get these guys. So then this converges actually. So when I'm writing this, I'm actually saying that 1 minus z over n, and I add a factor to make sure it converges, then this function, this guy, this function is a function with roots n equal to z equal to 1, 2, 3, so on. This is the function. If you add a z, it's fine. Anything else is something which is never 0, so some entire function like this. This is known as Weierstrass's theorem. Very practical. Whatever I've told you is extremely practical. You can just, write down the sign. Have you seen this before? Have you guys seen this before?
Only a class back in Fourier series, Professor.
Oh, you've done it in Fourier series, right? So he did a proof.
Yes, Professor.
Oh,
Like two, three classes back.
huh?
Two, three classes back. Yeah.
Oh, okay, okay. Yeah, I missed that. All right. So, how did he prove it? Did he prove it like this?
Um, no, no. I think he used something like some Fourier series expansion of some function of the teeth functions.
I see. I see. Well, this is not a proof. This is a guess. I'm telling you how to guess this. So anyway, so good. Yeah. So yeah, yeah. Bhatia and I like the same kind of stuff. Classical analysis. He knows exactly what is beautiful in math. But I don't. A lot of complex analysis courses don't get to here because they are struggling with just basic stuff. So this was a product known, I think, to Wallace. This is a very classic product. In fact, this is Euler used this to prove that summation 1 over n square is pi square over 6. So in fact, yeah, anyway. So the function. So this is just hand waving through some complex analysis. You can ask those. You can ask Pritam now to cover this theorem. It's a very practical theorem. Once you know that this is log business, it this power series expansion of log. Where is it? Yeah. If you know this power series expansion, you know exactly which terms to delete. And those terms you get from e raised per something, and that's Weierstrass theorem. So Weierstrass theorem is that if you have certain zeros, so you have zeros, z1, 0, z1, whatever, then you consider this function, right? Suppose let's call it alpha I, and you consider this product over I, and just to make it converge, you do whatever is required here to get cancel some of the terms from the log. So you add this exponent, and if these are all the zeros, the function can be written like this, modulo a entire function which is never zero. Entire function which is never zero is e raised per some function, some other function, g of z. So this is Weierstrass theorem. I mean, any analytic function, anything with certain zeros, you can just write it down. And this is exactly what they were doing in Euler products in Riemann zeta function and so on. So this is very, very classical. Anyway, so sine pi z. So coming back, I mean, I just have a few more minutes. I want to introduce the next product that we are working on. Sine pi z it's the simplest function with zeros at the integers, right? So it's at an arithmetic progression. So we consider the following function, tau z q, even though some people actually write p here. So 1 minus, well, why I put z, I can, well, doesn't matter. Let's put z. Okay, no, I don't want that. Other way around. I want q raised per k plus 1 over z. So it has zeros at z equal to, so this term, when q is equal to 0, k is equal to 0, then it has zeros at q raised per 0, and it has q raised per minus 1, q raised per minus 2, and so on. And this one has zeros. This is k plus 1 here. So 0 when z is equal to q square, q cubed, and so on. So this has zeros at q raised power all the integers. So it's the simplest function. I mean, uh, it looks like sine function, except that it has zeros at a geometric progression rather than, i.e., at a geometric progression. I mean, you can see why somebody like Euler or Jacobi or anybody would be interested in this, right? And we write it as in our favorite notation as zq over infinity and q over zq infinity product over here, and converges for absolute value of z less than 1. Now this is an analytic function except when z equal to 0. So again, this is something which you haven't done, but you will do. So I mean, many of you will do, and I think so. Ayush, are you also taking complex now?
Yes, Professor.
Okay, so everybody's taking complex. So why is it being offered next semester?
It's not being offered next semester, Professor.
Really? I okay. I thought it's being offered next semester. Okay, doesn't matter. This is an analytic function except when z equal to 0, and therefore and thus has a what is called a Laurent series expansion. Now, what is a Laurent series expansion around? It looks exactly like a power series expansion, except you're going from minus infinity to plus infinity. So 0 is not a it's not a, this is called a meromorphic function. So not holomorphic, but it's called a meromorphic. Um, yeah, and we will need to calculate. We need to compute what is AM, and partitions will be required. Okay, so I'll end here. Any questions on this? I mean, this is known as uh, theta product. I don't know what it's known as. Yeah, it's so we'll do some properties of this. This is very much like sine function. You may do a little bit of this in complex analysis, and you may, in fact, you may do a lot of it in Fourier analysis. So, I mean, for those people who are in Fourier analysis, you may see that. Have you seen it already?
No, Professor.
Are you doing elliptic functions at some stage?
Not yet, Professor.
Okay. Well, I mean, so all these classical subjects, they are all hanging. So all of us, most mathematicians got into math because of common, things which we liked. So they show up all over the period, and it's good because then students see them 5, 6 times. It's okay. So anyway, so we will be covering some theory of theta function, because I said that we will do um, some number theory, and this is an essential. So this comes up naturally in partition theory. So we will do this a little bit. This is a sort of building block of what are called elliptic functions. So what are elliptic functions? So you have a sine, it has one period, right? And elliptic functions have two periods. So looks like this. Suppose instead of one period, it has two periods. And it's a natural extension. There's nothing which has n periods. There are things which have zero periods, like rational functions. And these guys are they have the same value. Let's say this is a period, this is a period, and they have the same values if you break the grid anywhere. So it's a very natural kind of thing. There is no such thing with three periods. So this is it. Nice, some nice. And so a lot of number theory is around this guy. Okay, and they're very natural extensions in many ways. So like you saw over here, very naturally you're saying that sine is extended. This has got its zeros on an arithmetic progression. This has got its zeros on a geometric progression. So I mean, a very natural extensions. So I'm done. Any questions?